This week's activity is rapid prototyping, specifically the FDM process, which most people refer to as 3D printing. We're going to go through this week's activity in a similar way as to the previous weeks. I'm going to introduce the subject a little bit and talk about the machine and some of its parts. We're going to create a part. In this case, we're going to create a V-notched IZOD impact specimen. So we're going to take a digital model, we're going to load it into slicing software, which is software specifically designed for 3D printers, breaks the model up into layers, and allows us to pick certain parameters for that print. We're going to set up multiple parts in different orientations. We're going to print them, and then we're going to test them, since we are making a notched impact test specimen. That's very similar to the specimens that we've been making. The ones we did in the milling lab were Sharpie notched specimens. Those are more of a 3-point break specimen. They're held on the ends, and then the hammer strikes in the center. An IZOD specimen is held at the base, and then a hammer comes by and swings and breaks it that way. They're still very good indications of physical characteristics. We're going to print this shape in a number of different orientations and test them. And so we'll talk a little bit about the print parameters as we go through them. And then we'll test them and see if we can get a good idea of how those parameters affected the strength of the part. So the next step will be for me to introduce the 3D printer. This is the 3D printer that we're going to use in today's activity, and I just want to go over the parts of the machine and probably bring you in for a little bit closer look because while we're printing, the camera is going to be focused inside the build envelope. The machine consists of a heated glass build plate, borosilicate glass, so that it's very, very flat. We can build on it. We get very good adhesion as the plastic is deposited down, and it also keeps a flat surface then on the part because the build plate is so flat. You can see the print head at the top left, and the print head has 2 printing nozzles in it, and those are fed by the spools in the back here. There's only one spool on here right now because we're not going to use any filler material, but if we did, then one roll of material would feed up on one side, and then the other side would have the support material. That way the nozzle can switch between the 2 materials as it's printing. Once we've made our model and we've selected the parameters for the print, we'll load it onto a USB drive, plug it in. The machine will start heating the build plate and heating the nozzle, and then feeding the roll of plastic through the nozzle to make the part. Now, here we are in the slicing software. The software is provided by the company that makes the 3D printer. Well, really it does the same job that most slicing softwares do, and that is it's going to break the model we have down into sections and allow us to change the specific print parameters for that part. I'm going to import our part and scale it appropriately so that it's the size that's on the print that we have. And before we can select the print parameters, we want to locate it on our build plate. And also, since we want to print several of these, we want to duplicate this. We'll make 3 copies of the part, and we'll arrange them in different orientations. We'll put 2 in the vertical orientation with the notch up, and 2 with it on its side. And you can see that the parts are grayscale. They're grayscale because we've not yet assigned any print settings to it. So the part's not yet ready to print because we haven't told the printer how we want that done. We can set all the different parameters here things like wall thickness, the thickness on the top and the bottom of the part, the infill density, as well as pattern, and then a whole bunch of other things like the travel speed of the print head, build plate adhesion, which is a little additional material to help hold the part down, and then some other things that we can change pertaining to really unique parts. But if we just use the very basic settings that I have here and we hit slice, then it's going to break the part down, and what you'll see is each layer. There's a little slider here on the right that I can raise and lower to show you that the first layer of the part is here. So the nozzle will come down, create this outer boundary, and infill it so we have a solid face. It'll do that several times. According to this, the bottom layer thickness is going to be 6 layers thick. So it's going to make 6 of those. So if I go up to 6 count on the slider to the right, you can see that's the thickness of our wall. And then after that, it starts the infill pattern, which is a lower density pattern. This is just a simple crosshatch. And it's going to build that all the way up to the top here. It's the part is 50 layers thick. So to get some data from the impact strength that we'll get from different orientations, I'm going to take and rotate some of these parts so that we can see how that influences the impact strength. So here I have one with the notch up. We'll have one with the notch to the right. We'll use one. We'll turn with the notch to the left. And then we'll make one with the notch down. And that will pose some challenges for the machine, since it will have to create the notch without any supporting material in it. So I'll arrange these together. And the slicing software is going to give us an estimate of the amount of time it's going to take. This is 1 hour and 42 minutes. It's going to consume 23 grams of material, which the estimate here is it's going to be about 3 meters worth of material. So at this point, we can save it to a jump drive or USB drive, and then bring it out to the machine, and we can start the print. So now our print is beginning. The nozzle is preheated, and so is the build plate. So now the print head is going to come down, and it's going to probe the build surface a few times to establish that it's level. When it moves to the right, it's actually switching print heads. There's 2 nozzles in the print head, and we're going to use the one on the left, which it's using right now. So it's going to come down, and you can see it leaves just a little bit of filament because the nozzle is preheated. So it's going to move to the area we want to print, and it's going to probe the build plate a few times to make sure that it's level. There's a screw on the bottom right that we can use to make large adjustments in whether the build plate is level or not. But it's this small measurement system that it's doing right now that will allow it to calibrate the build plate itself. Once it's done checking the build plate for level, then it's going to lower the build plate and build up heat in the nozzle, and it will then re-raise the build plate and start building the part. So right now it's going to start preheating the left nozzle or the left print head to get ready for depositing material. That will take a couple seconds. There's a little bit actually. Leaves it there as it moves to the location it's going to start. And now it begins depositing plastic as it prints the first layer. going to move the camera up to a higher position where we can time lapse this. But you can see that it's created the outer boundary of the first layer, and now it's going in and it's filling in that framework with the first of those 6 layers that we talked about to create the hard lower surface of the print. So the time-lapse video you saw was of just one of our samples being made, and that's because the battery didn't last while I was recording all 4. So I showed you just the one time-lapse. But it's very simple to make multiple parts. They're still all done a layer at a time. So I want to make 2 more samples so that we have 6 samples to test. So 2 more, or 1 more orientation and 2 samples of that to do. So I'm going to delete 2 of these, and then I want to rotate these upright so that we print a couple in the upright position. And I think that that will give us, if not some interesting data in terms of impact strength, certainly the breaks themselves should show us something about the layer bond strength. So using the same parameters here that I printed them in the other orientation with, I can see that there's now 375 layers, so many more layers, but obviously they'll be a lot faster because they're smaller in cross section. So just to zoom in, you can see the same wall thickness as when they were printed horizontally and with the zigzag infill. Now, one of the issues that we can run into with printing these very narrow parts on end is that the bond to the build plate can break. And so there is an option in here for build plate adhesion. And if we look at this, we can select a number of options here. And the goal here is to try to give you a little bit more surface area to bond to the build plate. So there's several options here. A skirt, which will generate just a little boundary on the very outside. There is the brim, here, which is actually a default setting, and this will give us quite a bit more adhesion, but I think the most adhesion is going to come from the raft, which generates actually a pretty large, pretty thick surface, and then the part sits on top of it. We will have to break the part off, but I think that this is the right way to make these 2 samples to make sure that they don't crack off the build plate. So the next step will be to save this to a jump drive and get this started. At 1 hour and 11 minutes, I'll put a full charge on my phone and we'll see if we can do a time-lapse video of this. As we get ready to print our vertical orientation parts, I just wanted to give you a quick time lapse of exactly what's involved with loading one of these prints into the machine and getting it started. It's actually really simple. Once you have the jump drive that we saved our sliced file to, you can simply select it. It even gives you a little picture of the print there. Then it begins heating the build plate. It brings the print head over, and then this will look a lot like the process you saw earlier when I was showing you the start of the very first print. I'll now time-lapse this video so that you can see the build of the vertical orientation parts, and then we'll continue on to impact testing. Just for your own edification, I wanted to show you what it's like to remove one of the printed parts. You know, we added this raft here so that we'd get good adhesion, and of course it's very good adhesion. It's good enough that it makes it difficult to remove, but if you just work your way around with a utility knife, then they pop off pretty quickly. And then the plastic is relatively thin, and you can snap them off the raft, discard the raft, and here are our finished printed parts for the vertical position. Now, as we've done previously, we're going to impact test our samples. So here I have all of them. I've tried to mark them with a T so that I remember what the orientation is. But we'll start with the two samples that we printed with the top where the notch got printed on the side. There's the first sample. And that is 1.25 inch-pounds. And you can see the brake is very brittle. There's clearly no deformation like there was in the other laps. That was 0.75 inch-pounds. Next, we'll test the two samples that had the notch printed up. also 0.75 inch-pounds. And that was 1 inch-pound. Now we'll test the two that we just got done with, which were the vertically oriented samples. That was 0.75 inch-pounds. And that was also 0.75 inch-pounds. So in the normal course of this lab activity, I would give each group their own set of access to a 3D printer, and you would get to change and set your own parameters with the intent of maximizing the impact strength. However, what we see here is that with identical parameters, the orientation did not present us with a significant difference in impact strength, at least not one that we could pick up on a machine like this. When each group works separately, of course, you come up with your own combinations of variables and parameters, and we do tend to see some significant changes. But I think that because the parameters were the same, wall thickness, extrusion temperature, and infill density and infill pattern were all the same, we wound up with such minute differences that they simply weren't observable.